Welcome back. Now we're going to talk about functions that are not these simple functions. So in this class, we are going to study functions where the domain or range are no longer, the domain or range no longer lie in R. And so there's two different types of these functions. One of them that we're talking about, and that is going to be what we're going to talk about today and for the next couple of classes, are vector functions. All right, and another word for these are parametric functions. And the ones we're going to talk about later are called functions of several variables. So what we're going to do when we're talking about vector functions is we're going to have a function the book likes to use, instead of f, it likes to use r with an arrow on it because it's a vector. And what it does, instead of going from r to r, it goes from r to rn. What we can write down is that what we're doing is, what r does is it takes a value t in r, and the output of this function is a vector r of t. Right? Before, what we had is a function from r to r, and what the function did is it took x to out y of x, or x to f of x. Here we're taking t to r of t. All right, we'll develop this further, but I wanted to also just prime the pump in terms of saying, what are we going to talk about later? Later on, we're going to be talking about functions where the domain is a vector and the output is a real number. So in those cases, we would say f takes, for example, maybe we had a point x, y, z, and the output would be a single number, f of x, y, z. So that's something to think about for later. In that case, you're choosing a vector, you're choosing a point in 3 space, and the output is a number. But now we're going to be focusing exclusively on vector functions. And for vector functions, we're in the case where we put in a number and out comes a vector. All right, so what we're going to say is that the domain of R, the vector function R, is a subset of the reals, and the output of R is an n-dimensional vector. So this works in any dimensions. We can make this vector be in 2 space, 3 space, 4 space, 5 space. It can be in any size. But we'll mostly focus on dimension n equals 2 and n equals 3 because those we can draw. So, for example, if n is equal to 3, we might write r takes t to a vector of size 3, and we could write f of t comma g of t comma h of t. So which has 3 functions. So these are these standard functions, f of t, g of t, and h of t, that specify the x, y, and z coordinates of r of t. So we'll look at some examples of what these look like in a second. We've talked right now about the structure of this r, this vector function. It takes in a number and it gives out a coordinate, and this coordinate changes over time. This triple of coordinates, or this n tuple of coordinates, changes over time. All right, so let's mirror what we talked about before for just the regular functions. So unless otherwise specified, the domain of R is the intersection of the domains of f of t, g of t, and h of t. So what do I mean by that? So for example, consider this function. R of t is equal to ln of t, comma 5, comma square root of 4 minus x. This is a vector function. Oops, not 4 minus x, 4 minus t. This is a vector function. It takes in a number t, and it outputs a triple, where you plug in t into the first piece, the second piece, and the third piece, and you get out a vector with the x, y, and z coordinates specified. So what's the domain of this function? Well, what we need to know is the domain of ln of t, the domain of 5, and the domain of square root of 4 minus t. We need to know each of those domains, and based on what those domains are, we can say, well, what t is allowed in the whole function, it has to be allowed in each of those. Okay, so you should think for a second, pause the video if necessary. What's the domain of these functions? Okay, the domain of these functions, the domain of ln of t is equal to 0, comma, plus infinity. Right, you can't plug in 0 into the log, but you can plug in any positive number. The domain of 5 is negative infinity to infinity. That doesn't have any additional restrictions. And the domain of the square root of 4 minus t is, well, what numbers can we plug into this? You can't take the square root of a negative number, so t can't be bigger than 4. but anything else is fine. So negative infinity up to 4, and that's closed. So which values are allowed in all three of them? The intersection is 0, open at 0, closed at 4. This is the set of all points. This is the domain of R, or in other words, what t's are allowed to plug into R. Okay, so that's talking about the domain. Now let's think about the range of a vector function. The range of f, not f, R, the range of R, it's what's hit by this function. You plug in a t, what comes out of it? So the range of R is the set of all vectors v in Rn such that v is equal to f of t, not f of t, R of t, for some t in R. So right, it's any vector that appears if you plug in t for something. So this shows that the range is a subset of Rn. Okay, that's a little interesting. So it's a subset of Rn. Let's look at what that could look like. So if n is equal to 2, so if n is equal to 2, this is a vector in R2, it's in the plane. The range of R can be drawn as a curve or a collection of curves in R2. If n is equal to 3, the range of R can be drawn as a curve or a collection of curves in R3. And so what it's nice to think about is, so it's nice to think of t as time. And I think that's why we use t instead of some other variable. So it's nice to think of t as time, and r of t as the coordinates of a particle moving in time. So we've got t representing time, and r of t is keeping track of where the particle's moving in time. The curve of the range of R traces the path of the particle. Notice that this graph, it's not the same thing as the graph that we drew before. So this is not the same thing as, is not the same as before. Right, so before what we had was before we drew x comma f of x. And that was a curve through space. But now what we're drawing is we're actually only drawing the f of t, g of t, and if applicable h of t. We're not drawing t comma that. And so one of the consequences is that there's no vertical line test restriction. For vector functions. A vector function can go like that. That's allowed. And the last thing I want to talk about just is the theory and for this is that it's useful to think of this path. So useful to think of this curve or this object, this range. It's useful to think of this parametric curve. Let's write that. As a one-dimensional path through Rn. Right, the thing I just drew here with this curve here, it's lying in R2. It is in the plane, but it's really only one-dimensional. As you walk, you kind of only have one direction that you're going in. Right, we could put some arrows on here. For different values of t, we land at different points on this curve, and you're really following this one-dimensional path, even though it lives in a different dimension. If you're interested in that, you'll probably want to take some differential geometry or some manifold theory. So there's really cool higher level math talking about surfaces in higher dimensions. All right, let's stop here. The next video is going to have some examples, I promise, and some really cool pictures too. So stay tuned. Thanks.